Okay, in this video I'm going to continue on my tutorial series on thermodynamics and statistical mechanics. This is video number 21 and we're on the subsection of Einstein Solids. So in this subsection we're on video number 5 and I'm going to discuss the sharpness of the multiplicity function. In the previous video to this I discussed Einstein Solids 4 and we proved the formula for the multiplicity of a single Einstein solid. So why are we discussing the sharpness of the multiplicity function? Well, the point is we're trying to show that it is statistically overwhelmingly likely that the system will be in equilibrium when it is in its maximum multiplicity, or the state of maximum multiplicity. So we've seen in the past, that with two solids the maximum multiplicity will be when there is half the energy between both of the solids, and we'll see in this video that it's so tiny that is the probability that it'll be any other place, and that's why we say that's why we don't see any other state other than the state with maximum multiplicity. So before we do that, I'd just like to point out that we'll be using many of the tricks that we used in the previous video number 4, and the reason that I'm going to do all these explicitly is because they are pretty standard techniques in evaluating systems, and we'll see in a moment that if we get a very general expression for the multiplicity function, we're not able to look at it and see its physical significance. Whereas this is the formula we're going to derive or manipulate to get, and you'll see that, well, you might know already that this is a Gaussian function, which is, it has a physical meaning, whereas what we'll see in a moment, it won't. So we need to be able to learn how to manipulate functions to actually find or make visible their physical significance. Before we do that, I'm just going to remind you of one or two things which we did in the previous video. So we're going to say that the total number of units of energy in any solid is significantly larger than the number of oscillators in the solid. Thus the ratio of N versus Q is approximately 0. We used this fact in the last video. Also, the Taylor series of the natural logarithm of 1 plus or minus x is approximately plus or minus x. We're also going to use this, and we used that in the previous video. Remember, the way we did that was we divided out the argument. So we read a plus b, the natural logarithm of a plus b. What we did was we had the logarithm of 1 plus b over a, or log of ab, we'll say like that. Oh, it was b over a, wouldn't it be? b over a. So we had the log of b over a, and then we use the fact that log a log b is equal to log ab, and therefore here what we have is the log of a plus the log of 1 plus b over a, and here we can apply our Taylor series. Alright, so that's just a very quick reminder. Is there anything else that we need to remind you of? Just one more thing. Now, we'll see in a moment that I'm going to have, at some point, the natural logarithm of a times b. Well, two functions, a and b. But I will be manipulating b to become b prime. So eventually, this is going to become the natural logarithm of a b prime. But at no stage am I going to manipulate a. So the point is that because the log of ab is equal to the log of a plus the log of b, I'm able to manipulate b into whatever the hell I want, namely b prime in this case, and not touch a, and then in the end put them both back together as the log of ab prime. So what I'll do is I'll actually completely ignore this factor here, and I won't even write it in while I'm manipulating b prime, and at the end I'll just write it in. So I hope you understand why we can do that, and to be honest, I'm trying not to confuse the mathematics, so the fewer factors we have in front of you, the better. So we know from our study of thermodynamics so far that if we have two solids, A and B, and they are different temperatures, namely they might have Q sub A units of energy in Einstein solid A and Q sub B units of energy in Einstein solid B, we know that there will be a temperature difference because of the energy difference. Where we have a temperature difference, there will be a flow of energy as heat until there is an equal amount of energy between both. And we call this the position or the state of equilibrium. But that is defined as the state where we are at the maximum multiplicity. Alright? So in this case, where we have two different solids, what will be the maximum multiplicity? Well, think about it. If the total energy in units of Q is Q sub A plus Q sub B, the equilibrium position will be when Q sub A has Q over 2 units of energy, and that will be the same for Q sub B. In other words, there is an equal amount of energy between them, or they share equally the amount of energy. Alright, so we need to remember that. So let's go ahead and derive our expression. So we saw in the previous video that the multiplicity for a single Einstein solid, namely Einstein solid A, was E times Q sub A over N sub A to the power of N sub A, where N sub A was the number of oscillators in the solid. And similarly for Einstein solid B, we would have that it's E, which is just the number E, multiplied by Q sub B, divided by the number of oscillators in Einstein solid B, to the power of the number of oscillators in Einstein solid B. So let's make a simplification that the number of oscillators in either is the same. So instead of having N sub A and N sub B, we just have N. So that means we have this common factor which just allows the mathematics to flow a lot easier, so we get to see this physical significance. If we didn't make that simplification, we mightn't be able to get the physical interpretation as easy. So that's that's an example of the first step, or the sorts of steps you need to take. Next, we should know intuitively at this stage that the states, or the multiplicity, each of the states is independent of each other. So for that reason, it should make intuitive sense that the total multiplicity will in fact be the product of each of the individual multiplicities and not their sum, because that they're independent. So look, you can multiply this out, but we can rewrite this as follows: E over N to the power of twice N, and then we have Q sub A times Q sub B to the power of N. That's just a very, that's pretty simple, just use of exponents. Now we want to maximize this, or not maximize this, we want to manipulate this. Here is the trick. The trick is, it's difficult to manipulate this, but it's easy to manipulate logarithms, because they're really great for manipulating functions. But before I do that, I'd like to show you why we're doing this at all. We now have the multiplicity function for n, for two solids, or we'll say two Einstein solids. We have the multiplicity function, but with n oscillators in each one, and here it is here. But let's just go back up to what I wrote at the start, the formula we're trying to get. Now look at this. They mean the same thing. They will give you the same answers. But the point is, it might not be physically, or it might not be obvious what this even looks like. And to me, it definitely is not. I would have no idea what that looks like. However, you may know that this is a Gaussian function. You may not know, but you will soon. But if you look at this, you should immediately say to yourself, this is a Gaussian function, and this is what a Gaussian function looks like. But it's not immediately obvious when it's in this form. So we need to manipulate it. How do we manipulate something? We use logarithms. So we'll take the natural logarithm of the multiplicity. Now, as an aside, the multiplicity when you take the natural logarithm of it is the entropy. Now this is incidental in this case, because we're actually going to we're going to take the logarithm of the entropy, or of the multiplicity, dick around with it for a while, and then take the exponent of each side, or the exponential of each side, to get rid of the logarithm again. So the fact that at some stage we're calculating the entropy is just incidental. So what we have here is the natural logarithm of E over N to the twice N multiplied by Q sub A, Q sub B to the N close. Okay, now I said to you that I was going to manipulate one part of this logarithm and not the other. So let's call this, part B, call this part A. I'm not going to touch this. So this is the part that I'm just going to, discontinue writing, and in the end I'm going to write that factor back in, because the log of AB is the log of A plus B, and then when I dick around with a B, so it becomes B prime, then I can bring it back together. So from now on, I'm going to just not write that term for the moment, just for the analysis. So let's see what we have. We're trying to analyze Q sub A times Q sub B to the power of N, well, with the natural logarithm of it, of course. So you need a small bit of help here, because we will know that it's a Gaussian function. But the point of the Gaussian function is this, that it's only non-zero and over a very small range. So let's say we plot the number of units of energy in Einstein solid A. Well, then we know that the maximum multiplicity will be a Q over 2. And that's if we plot multiplicity versus energy units in A. So if I look here, well, I'm going to get 0 pretty much for the multiplicity. If I look here, I'm going to get 0. Unless you look in this very, very small range, you're going to get 0. So that means we need to look just right and left of the maximum. So the way I'm going to do this is, we know that in equilibrium there will be Q over 2 units of energy in A. So let's, instead of looking at the maximum, let's look slightly to the side of the maximum. Similarly, we know that there are Q sub B units of energy in B, or Q over 2 units of energy. So let's look slightly to the side of that. And we get this. So what we're going to do is plug both of these into this function here. Now you may realize that if you multiply the two of those together, what we in actual fact have is the difference of two squares. So if you don't see that, just multiply them out. But what we're going to have is Q over 2 to be squared minus X to be squared. And we're going to have this factor of n in the power. Alright, so what do we do now? Well, what I'm going to do is I'm going to bring down the n. We can do that because we're talking about logarithms. That's the first thing. What else will I do? Well, this is the case, I want to try and apply my Taylor expansion to this. So we need to essentially take out this Q over 2 to be squared factor. So we're going to get n outside of the logarithm of Q over 2 to be squared. And then we're going to have this outside of, because we're taking it outside, we're going to have 1 minus twice x over q to be squared, like that, and then close off the logarithm. Okay, this is what I showed at the start during my revision. So simply, well, maybe not so simply, this is n outside of the following: the natural logarithm of q over 2 to be squared plus the natural logarithm of 1 minus twice x over q all to be squared, like that. Close main bracket. Well, this is simply the factor I'm going to apply my Taylor expansion on, and it's just going to become minus outside of twice x over q to be squared. So I'm just going to write that straight in. So we're going to have minus outside of twice x over q all to be squared. Close main bracket, like that. Alright, now remember that we have our multiplicity, or the logarithm of our multiplicity, is equal to, the term that I'm not writing, which is the log of the term I'm not writing, plus this term here, plus n, outside of whatever, like that. So what I'm going to do is we're going to exponentiate the lot. That's what we're going to do. So let's go ahead and exponentiate the lot. Remember, if you have the reason this will work is because you have the log of e to the power of a plus b is actually the log of e to the a times log of e to the b, like that. So we're going to have the exponential of this argument here, which we no longer wrote, plus the exponential to this argument, to this power here. Alright? Okay, so let's go ahead and write the answer. So after all that manipulation, we're going to get back to the formula that I had written until I kind of rubbed it out. So we're going to get the following. The multiplicity, where two Einstein solids of each having n oscillators, is the following: e over n to the twice n, which we didn't write. Well, okay, we just ignored it for most of the analysis. Then the exponential of n log q over 2 to be squared, like that, times e to the minus n outside of twice x over q to be squared. And you might say to me, who cares? What do we actually gain from doing this? How do I know that that even means anything? Well, if you look here, no x dependence. In other words, it's essentially a constant of the system. So we said that this is the maximum multiplicity, and this is a Gaussian. And we know Gaussians are of the form e to the x squared over r squared. And that's exactly what we have here, e to the x squared over r squared of some form. So the point is, this is a maximum multiplicity up here, and then the Gaussian falls it off either side of the maximum. So how do we find out the full width at half maximum? So what is the full width at half maximum? Full width at half maximum is defined at the value when we have the maximum multiplicity divided by a factor of e. Or we define the full width at half maximum as the value when you've reduced the maximum by 2.71, I think it is, whatever e is. So how do we get that? Well, what we've just found is that we have the multiplicity is the multiplicity maximum times this Gaussian function. So we want to find out the value when the multiplicity is reduced by a factor of e, like that. So, you know, this is pretty straightforward. So let's look at now, by the way, this is because we're looking at the maximum multiplicity, of course, well, these two factors cancel here, so what we have is 1 over e is equal to e to the minus n twice x over q to b squared. Okay, and look, to be honest, I'm not even going to go into the analysis because it's pretty straightforward in terms of logarithms. But what we're going to find anyway is this value, the value of x for when we're at the full width of half maximum is q over 2 root n. So what this means, if I draw a really poor Gaussian, that value there is q over twice root n. This value here is omega max. And the point here is, and this is the whole crux of the evaluation, that if you were to actually plot this, okay, let's say, for argument's sake, if I was to plot it to be this big on paper, well then from here to here would be the bones of, you know, it would be the bones of thousands of kilometers. So if I'm trying to plot this, you know, the number of states, and I'm trying to plot it on a piece of paper, say approximately this big, the distance from the end point to the maximum is thousands of kilometers. In other words, it's highly unlikely that the system is anywhere other than the state of maximum multiplicity, and we know that a maximum multiplicity, that the value of energy between is for each of the solids is q over 2, where exactly half the energy has been shared. So the system will stop sharing energy as heat when the temperature is the same, in this case q over 2 units of energy. The bottom line up front, well, the bottom line up last, excuse me, only a tiny fraction of the macro states in a large system are accessible. Okay, that's all I've got to say about that. I hope you found that intriguing. So thanks for watching. Please pass it on to your friends, subscribe to my channel, and if you found that interesting or you're in a good mood, you might also click on an ad. Thank you.